When protective relays are configured correctly, a fault clears in fractions of a second, leaving the equipment unharmed. When those settings are wrong, the internal coils overheat, deform, and eventually melt. This graph plots the ANSI Category 3 damage curve, defining exactly how much through-fault current a transformer can survive over time. The steep upper slope represents the thermal limit, where long-duration faults cook the insulation, while the lower section tracks the mechanical limit, where massive, sudden fault currents physically warp the copper. To protect the equipment, we program the overcurrent relay, the 51 element, to trip the circuit before the current reaches that damage curve. We maintain a deliberate time gap, typically 0.2 to 0.4 seconds, ensuring the relay acts first. In a YY transformer, the current traveling down the external power line flows directly into the internal winding. Because the line current the relay sees is identical to the winding current the damage curve protects, the coordination math is 1-to-1. But industrial networks rarely use YY configurations. If you assume that 1-to-1 ratio on different winding geometries, your relay will be looking at the wrong numbers, entirely compromising your safety margin. Most industrial applications rely on the delta Y configuration, noted as a DY-N11 vector group. D indicates a delta primary, and Y a Y secondary. The number 11 is a clock multiplier. Multiply 11 by 30 degrees. The secondary voltage lags by 330 degrees. ANSI curves track internal winding current, but relays monitor the external line. In delta configurations, line current splits entering the coils, meaning measurements mismatch. Plotting line current directly against winding damage curves mixes scales. Your margin vanishes, and the curves dangerously intersect. Without translating external line current to match internal winding current, the relay operates completely blind to the actual physical stress building up inside the transformer. To fix this, we must translate the primary winding damage curve onto the primary line current base. This puts both the relay settings and the transformer limits on the exact same scale. Since line current entering a delta winding is the square root of 3 times larger than the current inside, we multiply the damage curve coordinates by that same factor. This shifts the curve right, reflecting the higher line current threshold required to reach physical limits. Let's apply this. If you encounter a transformer labeled DD0, what is the phase shift and does the damage curve need to be shifted? A clock multiplier of 0 means a 0-degree phase shift. However, since the primary is still a delta winding, you must multiply the damage curve current by the square root of 3 to perfectly align your relay. The geometry becomes even more critical during an unbalanced fault. If a phase-to-phase fault occurs on the secondary side of a delta Y transformer, the physics of the delta winding force the primary B-phase line to carry twice the load of the individual windings involved. This chart details a B-phase winding damage curve specifically reflected to the B-phase line current using a factor of 2. Because the B-phase relay sees twice the current of either winding, the curve must be mapped to account for this specific asymmetric fault geometry. Mapping asymmetrical faults is mandatory. Without it, the relay averages the load, failing to trip before an overloaded winding reaches its physical breaking point. The correct protection workflow follows 3 steps. First, read the nameplate vector group to determine if your primary winding is a delta or a Y. Second, apply the math. If you have a delta primary, multiply your damage curve current values by the square root of 3, so your relay settings and your damage curve share the exact same measurement base. Third, verify your plot. Your inverse time over current curve must sit safely beneath the newly shifted damage curve, preserving your intentional time delay margin. Keep these 3 rules in mind. Vector group numbers multiply by 30 degrees for phase shift, ANSI curves dictate your hard physical limits, and delta primaries always require a mathematical shift to match line current to winding current. Calculating these geometric shifts separates reliable engineering from catastrophic equipment failures. Next, we'll look inside the tank, using dissolved gas analysis to catch degradation before a fault ever triggers.